Okay, so our new topic is scalars and vectors. The mathematical concepts and trigonometric relationships you learn in previous sections will useful, actually essential for you to work on scalars and vectors. Scalars are quantities which is like a number with a unit. For example, temperature 100 Celsius or 74 Fahrenheit. Speed 100 miles per hour. So magnitude and a unit. On the other hand, the vectors. Vector is a quantity deal with both magnitude and direction. For the example, force 12 Newton. Newton is the unit of force, and also we have to say the direction 12 Newton to west or 5 Newtons to right. So magnitude and direction. So vectors has magnitude and direction, both magnitude and direction. So scale quantity is just a number, sometimes with a unit. So those are scalar quantities, and we can add similar scalars like 100 Celsius to, you can add 25 Celsius, 125 Celsius. Okay, and similarly, if the vectors are in the same direction, 12 Newton to west and 5 Newton force to west, these are vectors with same direction. Therefore, you can add and say 17 Newton to west. If this vector is 5 Newton to east, then you still can add because they are in the same line. So you can write this is 17, this is 7 Newtons to west. So if the vectors in the same direction, you still can add, but we're going to learn in next few chapters, if sections, if the vectors in angle, if two vectors in a certain angle to each other, then how you can add them. Okay, so how you represent a vector? We use an arrow to represent a vector. So length of the arrow, let's say 3 units, and also arrowhead pointing the direction of the vector. So magnitude represents the length of the arrow, and the arrow head represents the direction. So here's another vector. It's another vector. So the length of the vector is proportional to the magnitude, and the head points the direction. As I briefly mentioned at the beginning, it is necessary to add one vector to another. So the most simplest case is if you consider two vectors in the same direction. Let's say 3 Newton to your right and another 2 Newton to your right. So you can say, you can add these two together. So this is, you have to follow a certain pattern. So this is starting point or tail, this is head of this vector. So you can take either one of these. Let's start with 2n. Head, tail of the first vector you chose, which is 2n. Head of the first vector you use, and then you can bring the tail of the second vector right onto the head of the first vector. Tail, head, tail, head. So your final vector is tail of the first vector to head of the second vector. This is the head of the second vector. This is the tail of the first vector. So this one vector represents the combination of this vector plus this vector. Okay, let me give you another example. Let's consider another vector, 3 Newton to right, and let me use a different color. Five Newton to left. So if you add, this is your first vector, this is your second vector. So if you add 1 to 2, you just start with first vector. You can draw like this. Let me make more room. This is your first vector, 3n. This is tail, head, and then you bring the tail of the second vector to the head of the first vector. So which means you draw like this, like that. So this is the tail of the first vector, head of the second vector, tail of the first vector to head of the second vector. So your final vector is tail to head. I will use a different color and I'll put 2 arrows. This is your final vector. So A1 plus 2 gives you a vector. The magnitude is, this is 5, this is 3, 2 newtons to left. So direction of this arrow shows the direction. So this is your final vector, resultant vector. Okay, let's now assume if you have two vectors to a 90 degrees each other. So let's say you have vector A like this. You have another vector, vector B is like this. Okay, so you can start with A or B, it doesn't matter. So let's try with B. So this is your first vector you chose, vector B. This is tail, head. So now you bring the tail of the vector A, second vector, to the head of the first vector you chose. Something like that. Tail, head, tail, head. So this is your vector A. So your final vector is tail of the first vector you chose to head of the second vector. So these two are identical. You can use A plus B or B. You still get the same resultant R vector. Tail to head, tail to head. So you have to follow the same combination. Tail of the first vector to head of the first vector, and then bring the second vector, tail of the second vector, to the head of the first vector. So if you have two vectors or any multiple number of vectors, it can be 4 or 5, you keep adding one vector to the other, follow tail to head, tail to head. So the resultant vector is the combination of all the vector additions. You start with tail of the very first vector you chose to the head of the very last vector you chose. Let me show you another example with 3 vectors in the next slide. Okay, let's use 3 different vectors and see how you add these 3. Let's say you have one vector to right. Let's say this is 2 Newton, and you have another vector south to north, 3 Newton, and then you have another vector from to left, let's say 5 Newton. So this is vector 1, vector 2, vector 3. So you can add 1 plus 2 plus 3 or 2 plus 3 plus 1, any combination. Let's say let's say 2 plus 3 plus 1, vector 2, vector 3, vector 1. So let's start with vector 2. Vector 2 is going up. So it's a red color vector. So okay, so this is that vector. Tail, head, and then 2 and then 3, vector 3. Tail of the second vector, you bring it to the head of the very first vector you chose. It's a purple color, so let me use a okay, try again. So this is the tail of the vector 2, head of the vector 2, and then you bring tail of the vector 3 to the head of the vector 2, and now you have head here of, and then you bring tail of the vector 1, which is this, to head of this. So I will use black. This is your vector. This is your vector 1. Okay, so this is your start. You have to choose the very first vector. That's your start. Or the tail of the very first vector you choose, which is number 2. And this is the very last vector you choose. This is the head, which is your finish. So your resultant vector is the combination of 2 plus, if when you add 2 plus 3 plus 1, your result is start of the very first vector to the finish of the very last vector. It's like this. I will put 2 arrows. This is the magnitude. If you draw these 3 vectors to a certain scale, and if you measure the length of this vector r, that is the result as a addition of 2 plus 3 plus 1. You can add 1 to 2 to 3 and you still get exactly the same vector. So now let's use some numbers. So now we learn how to add vectors. Let's say you add a to b, and if the length of or the magnitude of vector a is 6 meters to right, and magnitude of the vector b is 2 meters, and the direction is south to north, and a plus b is, this is the vector. So to get the magnitude of this vector, You can use Pythagorean theorem, you know, the mathematical relationships you learn. 6 square plus 2 square and square root, which is equal to r. And also the angle, which is the direction, you can use sine or cosine or tan trigonometric relationships. You know, you use, you know, if you use tan of theta, which is opposite to this angle, 2 divided by 6. So inverse tan 2 over 6 is the angle. So now you have the magnitude using Pythagorean, and also you have the direction. You can calculate using these trigonometric relationships, and then you can have the resultant vector. Okay, so vector addition and subtraction. You know, subtraction part, we what we do is we multiplied a vector by -1. So if I have a vector, let's say 5 newtons to right, if I multiply this vector by -1, you will get a vector. Magnitude is still same, but you reverse the direction, 5 Newton. So in this example, you add two vectors, A, tail to head, and then B, tail to head. So A plus B is equal to C, which is vector C, tail to head, tail head, and tail to head of the resultant vector. So if you multiply this vector by -1, it reverses the direction. Now you have two vectors, tail of vector C, head of vector C, and tail of the vector -b, head of vector -b. So you now add in vector C to -b, tail, head, which is equal to vector A. So when you multiply by -1, or when you reverse the direction, it becomes a negative vector, or opposite direction vector. Before I go to the next topic, I want to summarize the uh, vector additions we learned in the previous couple of sections. So if you have two vectors in same line, so 2 Newton, 3 Newton, when you add 2 Newton vector to 3 Newton vector, you use tail to head, and you end up getting a tail to head 1 Newton vector. And if you have another two vectors in a certain angle, let's say 3 Newton, 3 Newton, when you add, you take one vector, tail to head, and then bring the second vector, tail of the second vector to head of the first vector, and your resultant vector is this, tail of the first vector to head of the second vector. This is your resultant vector, 3n, 3n. So this is one way of adding vectors. And the next topic, we're going to use components of vectors. We can use components of vectors. For example, now if I have two vectors, I can add these two, and you can have one vector. So you start with 3 Newton and 3 Newton vectors, one to right, one north, south, and you will get a resultant vector like this. If I give you a vector to an arbitrary angle, let's say you have a 3n Newton and 30 degrees to horizontal direction, you can write these two vectors in terms of one horizontal vector and one vertical vector. And you can use sine, cosine trigonometric relationships to find out the horizontal component of this vector and vertical component of this vector. So basically this one vector you split to two vectors, one in horizontal, one in vertical. So it's sort of opposite of what we did. So we start with horizontal vector and vertical vector. Once we add these two, you get one vector to an arbitrary direction. Now you do the opposite. You have a vector to arbitrary direction and you split this vector along x direction and y direction, and you get uh, using these trigonometric relationships. The reason is we know if we have multiple vectors along any arbitrary directions, each of those vectors we can find their horizontal components and vertical components. We know if there are horizontal components, like it may not be in the same direction, it can be opposite direction, but we still can add those two, all the horizontal components together, and we add all the vertical components together. So once you add all the horizontal components together, you will get one vector along horizontal direction, and similarly when you add all the vertical components, you will get one vector in vertical direction. So now you have two vectors, then you can use the simple A plus B equals C triangle, and you can find the vector. So let me give you more details in this concept in next few slides. Okay, so in this example, you see a vector R along some direction, you say theta. So you can write this R vector along x direction and y direction. We know that if you add this x component and y component, you will get R. So x and y are called x vector component and y vector component of this vector R. Okay, so x, because this is x direction, therefore component of R along x direction, we call it x vector component. Component of vector y along y direction is the vertical component of R. Okay, so we have a vector A 30 degrees to the horizontal direction. So we can use cosine to get the component of A along x direction. We use it AX because AX means component of x component of vector A. Therefore, we put x. So A is the initial vector which has a theta degrees to horizontal direction. AY is the y component, vertical component of vector A. Y means vertical, y direction component of A. So if you add AX, which is a horizontal vector, plus AY, tail head. So AX plus AY, you will get A. So AX plus AY, you will get A. In the previous page, we wrote vector A is a vector A, small letter AX plus AY, vector AY, vector along A. So instead of writing AX, I can write magnitude of A and multiply by a unit vector along x direction. Magnitude of AY times unit vector. So this means a vector, and its magnitude is, if you take the magnitude of the unit vector y, if you take the magnitude, which means magnitude, which is equal to 1. So it's a vector along y direction, unit vector along x direction. So you get the magnitude along x direction. It's another way of writing vectors. So basically, A equals magnitude of AX times unit vector along x direction, magnitude of AY times unit vector along y direction. So this is same as A. This is bold letter A. X, AY. Or I can put an arrow, then you know it's the vector AX. A equals AX, vector AX. So these are identical. So whole term AY times unit vector Y is the same as vector AY. It's just another notation. Okay, here's an example. There's a vector R and its magnitude is 175, 50 degrees to horizontal. Find X and Y components of this vector. So now you can use trigonometric relationships to use the X component. We know this angle is 50 and horizontal component is adjacent. Therefore, we can use cosine of 50, which is equal to the length of the adjacent side, which is X, and hypotenuse, which is 175. Therefore, X is 175 cosine 50. So once you get the number, you will get X equals 175 cosine 112 meters, 112 meters. This is just the magnitude, and the direction is unit vector along X direction. So this is your vector X. Vector Y, this is the opposite direction, therefore you can use sine. Let me use a different color. Sine of 50, this is opposite is Y, and hypotenuse is 175. So Y equals 175 sine of 50. So you will get 134. So Y equals 134 and multiply by unit vector along Y direction. So therefore R, you can write X component 112X hat plus 134 Y hat. That's the unit vector along Y direction. Okay, so just like this, so you can put units if you want. So 112 meters X hat plus 134 meters Y hat. Y hat is the unit vector along Y direction. X hat is a unit vector along X direction. Okay, here's a more advanced example. So now let's consider two vectors, vector A and vector B. Both are some sort of arbitrary direction with respect to horizontal axis. Vector B has an angle which is not equal to the angle with horizontal axis of A. And now when you want to add A to B, you can draw tail to head of B, and the final vector or resultant vector is tail of vector A to head of vector B. This is vector C. So A plus B is C, and the second method is the component method. So you can use the component of vector A along X direction and vector A along Y direction, and similarly you can take the component of vector B along X direction and vector B along Y direction. We know if you have two vectors in same direction, you can add this one and this one together, and you can write the resultant vector. Similarly, now you have vector AX and also vector BX. So you can write BX like this, AX here. So this is the resultant vector of AX and BX along horizontal direction. And similarly, you can add Y component of A, which is this AY, and Y component of B is BY. So you can add AY to BY, and this is AY plus BY. So this is AX plus bx. So if you add ax plus ay, bx plus by, which is b, the c is a plus b, a is ax x hat plus ay ay y hat. Vector b is bx x hat plus by y hat. And now you can use x hat similar. Therefore you can write parenthesis ax plus ay, I'm sorry, ax plus x component of a, x component of b multiplied by unit vector along x direction plus by ay y hat. So x component of vector a and b along x direction, y component of vector b and a along y, which is equal to vector c. That's the second way of adding vectors. The first way is just draw the vectors to a scale following tail to head. And the second way is the component method. You get the components of all vectors along x direction and components of all vectors along y direction, and then you add all x components separately like this, ax dx and ay bi y, and then your final vector is x components, total x components along unit x direction, and components of y, vector y, along y direction. Okay, let me do another example. Let's consider three vectors. Vector A, which is equal to, let's say, 3. And then you can write components of A along x direction, component of A along y direction. This is A, x, A, y. So you can use sine, cosine. Let's assume this angle is 60. So cosine 60 equals ax over hypotenuse, which is 3. Ax equals negative 3 cosine 60, which is 1.5. Where the negative sign? Because it is pointing towards negative x direction. This is your positive x direction. This is your positive y direction. So anything opposite to that direction is negative. Ax is negative 1.5. X hat is along x direction, but it's a negative because it's opposite direction. Similarly, you can write sine of 60, which is opposite, which is ay divided by 3. So ay, vector ay, this is vector ax, equals 3 sine 60, which is a positive number because it's in positive direction. So 3 sine 60 is 2.59. This is one vector, and now let me use a different color. Vector b is 3x hat. It is along horizontal direction, therefore we don't need to do anything because it's if it is a vertical, same thing, it's has only one component along x direction. 3x hat by, there's no y component, therefore I can put 0. And the third vector is, let me draw a triangle again. this is vector C, which is 4, and this is Cx, this is Cy, this angle is 30, so you can write Cx equals, if you take cosine, you can write Cx over 4, therefore you can write 4 cosine 30, which is Cx vector. Cx equals 3.46 x hat along its direction. Cy again, notice it's pointing downwards, therefore it's a negative number. 4 sine 30, which is negative 2 y hat. So now you have x and y component of vector a, b, c, and I can write a table a, b, c. Let me make it with a little bit more room to write vector a, vector b, vector c, x component of a, b, c, y component of it. So x component of vector a we already figured out, negative 1.5 magnitude, and y component is 2.59. X component of vector b is 3. There's no y component, 0. X component of vector c 3.46. Y component of vector c negative 2. So if you add, now all these x components are in x direction, therefore you can add, because it's in one line, you get 4.96. And y components you get 0.59. So now you have ax plus bx plus cx, which is equal to, if you consider as vectors, 4.96 x hat and ay by plus cy, which is equal to 0.59 y hat. So if you add, so if you draw this ax plus bx cx, it's a triangle like this, 4.96, and then a very small horizontal length, phi 9, and along horizontal vertical direction, and your resultant is this vector, which is, I'll put r, which is 4.96 square plus 0.59 square root, which is the vector r, and you can measure the theta, which is the direction. So use tan theta, which is 0.59 divided by 4.96, and you can take the inverse, and this is how you solve this kind of problem. So when you can have 3 components, 4 components, or any number of components, you just need to figure out the x components of those vectors, y components of those vectors, and then you can make a small table like this and add all the x component of given vectors and get a number. And similarly, you add all the y components of those numbers, and finally you have 3 vectors. Now you end up having only x components and y components, just 2 vectors basically, x direction vector, y direction vector. So if you have 2 vectors which have 90 degrees, you can bring tail to head, and then you can go back to your principles and figure out the the resultant length using Pythagorean, and also using trigonometric you can calculate the angle. And the lab 1 I assigned to you, you can use similar. There are 3 different ways of doing lab 1. The very first one is the the graphical method, which means you have to draw all 3 vectors to a scale and then measure the final vector length and the angle. And also second method is just like this, just adding components. When you do the second method and first method, you still get the similar results or exactly the same answer.